So can you see the presentation?
Yeah.
Okay. So very short about me. My name is Fredrik Lind. I'm working at a European utility company called the E.ON, where we are roughly 70,000 employees working in 15 different countries in Europe. I also have a background as a researcher, and I'm a colleague with Professor Bo Lechner and Professor David Payares. So I've been working at Chalmers for 12 years, but now I have started to work at this utility company instead. And today I will discuss some about active beds and what we mean with this. I will turn my camera off because I think it will be working better. Okay, so to start with, there are a lot of important parameters to operate the fluidized bed boiler. And in Sweden, we are commonly using both stationary bed and bubbling fluidized beds and circulating fluidized bed. In fact, we have more of those bubbling fluidized beds. When you operate those boilers, the choice of fuel is of course important. And it's important because you need some pre-treatment of the fuel. The more heterogeneous, so the more ash you have in the fuel can demand the more complex pretreatment system. But it can also be so that you need some additives for some cases, for example, to handle ash or such. Solids and fuel mixing is important because it also handles the heat transport inside the furnace and also with external heat exchangers. We can, for example, see in some of our boilers today that we have an increasing heating value of our waste products. It actually becomes quite difficult to handle the heat balance in the furnace. So there is always a change in this. We also have the mixing of air and fuel, which is really important. And this has been developed a lot during the years. Also, bed materials and other ash-related effects can have great effects on the system. And this is where I will focus my presentation today. And I will discuss those two parts from perspective of emission, corrosion, agglomeration, and temperature profiles. And also how actually active bed materials could in some way make a difference for this. Okay, so if we start with the fuel properties. As I said, the fuel is of course a really important design parameter. And you have to take into account moisture, volatility, ash, and heating values. And this will then be put into a heat balance, but it will also control the flue gas flow because some fuels are more problematic to burn and you will need more oxygen in the fuel, oxygen in the furnace to actually combust the fuel in a proper way. But due to some ash issues, you can also have to choose different steels or alloys in your superheaters to avoid high temperature corrosion. And due to the actual ash content of the fuel, we might also need to have different types of ash handling systems in the boiler system. So with that said, an optimal design could in some way probably decrease the fuel flexibility. One thing which is quite common or which is well known is that biomass and waste, they change over time the fuel properties because they can be that we actually follow fuel cost. There can be seasonal variations of the fuel. And one example of this is actually a quite new build boiler in Sweden, Stockholm, which was taken into operation in 2018. It's a quite large biomass-fired boiler, 400 megawatt thermal. It has also actually been equipped with a pilot CCS these days. After 1 year, they realized that they would like to change the fuel mix and add on 50% of recycled wood, waste recycled wood. And this, in fact, led to that they have to rebuild totally the ash system if they will go for this. The mixing of air and fuel. There has been a lot of changes in this way, where you can actually feed air in many positions, increasing the possibility for the fuel to meet the oxidizer. We also have much faster O2 analysis today, which gives somewhat the system a chance to react on a change in the fuel feeding. We also discussed today artificial intelligence and how we can learn from big data and how we can actually apply this to get a more robust and fast system. In other words, we can implement quite advanced control systems today. I would like to say that this is a picture of a state, or it's actually a screenshot from the operation of a state-of-the-art CFB boiler in 2016. This was built by Foster Wheeler. It's a 115 megawatt. It's a really robust boiler operating with biomass, peat, and recycled wood. It has a lot of fuel feeding. Instead of fans for the air feeding, it has air compressors, which can increase the pressure of the air into the boiler, meaning that you can penetrate more into the furnace. It also has a quite advanced control system. So questions, does this work? Yeah, it works good, but sometimes you have CO violations. You could have high furnace and cyclone temperatures due to you have uncombusted fuel going into the cyclones. And this can also create sometimes that you have a lower operating time than you actually prefer. We've seen in our boilers that we have somewhat maintenance experience that comes back, or maintenance issues. And so, for example, in one of our 75 megawatt CFB municipal solid waste 5 boilers, we had a problem with the vortex finders in the cyclones. Due to that, we have sometimes high temperatures due to uncombusted fuels going into the cyclones. We also have some corrosion issues from potassium and sodium, and erosion from the bed material itself. We can also see that our Intrex steam superheaters in the bed's loop seals are affected by corrosion and erosion. And actually together, corrosion and erosion can be a really big issue, because as you have the corrosion, you create this protective layer of an oxide on the tubes. But then you have the erosion from the bed material that all the time takes away the protective surface. So if we talk about bed materials are, the object of bed materials is to secure the heat transport. And that is if it's not enough ashes in the fuel, so that can be the bed material. And it should also be the right particle size. A bed material should have high abrasion resistance, but it should also have a low erosion impact on the boiler material. There are a lot of different bed materials, and those have different properties. They could be active, and they could need some things to be activated. And we know that alkali interactions could lead to agglomeration. And as far as I know, on the research basis, there has been lots of tests of different bed materials. In Sweden, for biomass and waste combustion, the silica sand is still absolutely the most common bed material. And the price is somewhat $50 to $65 per ton of this bed material. So, some conventional fuels and bed materials in fluidized bed combustion. If we start with coal, you have the characteristic of your fuel is that you have a rather high heating value. You have a lot of the ashes are actually bound to the minerals in the ash. The bed material is the fuel ash and also sulfur capture agents like limestone, for example. The bed regeneration rate, or the time the particles actually spend in the furnace, is very much controlled by the fuel ash content and the bed height. So simply when you increase the bed height, when you introduce more ash, you take out bed material. And in that sense, you have the bed regeneration rate working. If we discuss biomass, it's a fuel with a low or medium heating value. It has a lot of volatile carbon and also volatile ash fraction that could be really problematic. So in those kind of systems, there are roughly 80 to 90% of the bed material is actually minerals of different kinds, and only 20 to 10% of the bed material composition is actually fuel ash. In biomass combustion, you commonly would like to have an great exchange of the bed material, or you need to exchange the bed material because the alkali is also stuck on the bed material. So the silica sand in that case work as an alkali getter. And what you do is that you put in roughly 3 kilograms of silica sand per megawatt hour. So rule of thumb is that you put in this and then you just remove bed material according to keep the bed height in the furnace. If we discuss waste, it's also low to medium heating value. It's a lot of volatile carbon and it's a lot of volatile ash. And now you also introduce new ash components like heavy metals and other stuff that could actually be really problematic from a high temperature corrosion point of view. In the case of waste combustion, it's actually only 20 to 40% of the bed material that contains the mine minerals. The rest is the fuel ash. And this is also something that you would like to control. As you have more problematic ash components in waste combustion, you would like to have a higher degree of regeneration. So you more or less double the amount of silica sand, fresh silica sand per megawatt hour. Of course, it also depends on the quality of your bed material or your ash handling system after the boiler. I will discuss this some more later on. But the focus of my presentation will be in biomass and waste. So silica sand is the cost. In Sweden, we consume roughly a little bit lower than 200 kilotons of silica sand each year for the purpose of combusting in fluidized beds. This actually corresponds to 25% of the total amount of silica sand that is extracted per year, and a price tag of around $10 to $12 million each year. So this is just what we put in as a bed material. Some trends in Sweden and also Europe is that there is an increasing demand to combust waste fuel, cheap fuels, and also more complex fuels, biomass fuels. In Sweden, for example, we are now phasing out the last coal units, and we also reduce or even take away all the peat combustion. This is seen also as a fossil fuel in Sweden, or at least there is a CO tax on this. I can also see in industry that energy stakeholders, both from the energy users and energy producers, they're starting to discuss or request a strategy for carbon capture and storage. And in Sweden, there's a lot of discussion about carbon capture and storage. However, since there is a lot of existing infrastructure, there is a lot of discussion in post-cleaning by amines or hot potassium carbonate cycle, which has been used, for example, by Stockholm Exergi, a Swedish utility company. So what is an active bed material? An active bed material is something that should introduce more benefits to the combustion system than the ordinary bed material. And in this case, I will discuss something which we call oxygen carrier aided combustion. This was a concept that we developed at Chalmers, and simply is that you have a bed material that also can do more things than just being a heat carrier. Of course, it's not completely true, because silica sand, for example, in biomass and waste combustion, will also take up ash, which is good because then you have less ash in the volatile phase that actually ends up on superheaters or heat exchangers later on. But one of the major points with oxygen carrier aided combustion is that you use a bed material that can transport oxygen inside the furnace. So you can simply take up oxygen and transport oxygen. And there can also be other effects by ash. For example, that the ash is not ending up on the surface of the particle, but it instead migrates into the center of the particle. Commonly, we discuss those from a perspective on natural ores. So this was also discussed a bit by Bo Lechner with chemical looping combustion before. But in this case, we do everything in the same furnace or in the same reactor. So in the furnace of an existing CFB boiler. So what is happening is that the bed material during redox reaction can take up oxygen when there is oxygen present. And then it can be transported around in the furnace until it will come to a place where you have a reduction atmosphere, meaning that you will have gaseous fuel somewhere, which will react with the oxygen carrier. And the oxygen carrier will leave the oxygen and you will produce water and carbon dioxide. So this will be a cycle. The bed material will go back again and be oxidized, and it will be more or less smoothen out the oxygen profile in the furnace. In our case, we have looked in 5 different metal oxides, which has been tested in scales bigger than 10 megawatt, because there's been a large research of this at Chalmers. And I think that Anders Lingfeldt says that there is more than 500 different metal oxide that has been tested for oxygen carriers. So in our case, I will discuss something about Improbed. Improbed is also the company that I work for. And this is based on using an oxygen carrier. I will discuss this a bit more later. In our case, the Improbed is based on the metal oxide ilmenite, or the natural ore ilmenite, which exists in different, like rock ilmenite, for example, which is very common in Norway and in Canada. Sand ilmenite, which is, for example, present in India. We also use some LD slag, which is actually a waste product from the Swedish steel industry. And an ore provided by Sibelco Nordic, which is containing a lot of manganese. So why use those kinds of ores? Yeah, because the iron and the calcium and the manganese can transport oxygen. So it can. I think there is someone having a mic. Okay. So to give you some idea of what we have been doing with this kind of research, we have been working in the scale from 12 megawatt, which is the Chalmers CFB research boiler, up to the scale of around 170 megawatt boiler. And as you can see, that we have tested a lot of different fuels, everything from really nice fuel from wood chips up to municipal solid waste and peat, and a lot of also recycled wood has been tested. Most of the test has been done with Improbed, which then is based on ilmenite with a certain characteristics. So I will focus on the ilmenite from now on. And as I said, ilmenite is a natural occurring ore. It has a higher density than silica sand. As you can see, roughly 2,600 instead of 1,600 kilograms per cubic meter. And this, of course, changes somewhat the properties and the fluidization. So you have to adopt the particle size and so on to the fluidization. It has been shown that it's less abrasive than silica sand, and it's less prone to agglomerate than silica sand. And another quite important thing is that it is possible to separate from ash by a magnet field. This was something that Professor Lechner mentioned before, that this could be advantageous to be able to separate the oxygen carriers from the ash, so you can reuse them. The price, well, yeah, it's quite more expensive than silica sand. It's 70 times more expensive per kilogram than ordinary silica sand. I would like to discuss something about ash interactions with ilmenite. This is actually a SEM picture from some of our tests performed in the Chalmers boiler. And this is ilmenite particles. You can see that if we focus on the potassium, which is one of the critical components in biomass combustion, potassium together with chlorine will form species that will induce high temperature corrosion. So what you can see is that the potassium is starting to form after some time of operation, 6 hours around the particles. And then after 48 hours, you can see that it actually migrates into the center of the particle. And that's quite interesting compared to silica sand when it ends up in the outer shell of the particles. You can also see in this case where we've had sulfur, that the sulfur seems to follow the potassium into the center of the particle. So why is this interesting? Yeah, it could be one of the backgrounds to that we had this behavior. This is from the Chalmers boiler, when we usually soot the convection path, in this case the economizer. So you blow steam into the economizer, get a reading of the ash formed on the tubes, so you can have a higher heat transport. So this is the temperature after the economizer, and you can see that on a daily basis we do this sooting behavior to get back again to the former heat transport. And this is with silica sand. And when we did the first operation with ilmenite, we stopped the boiler, we completely changed the bed material to ilmenite, and we made the same thing. But in this case, there were never any temperature increase after the economizer, even though we were operating for three weeks in this case. So we stopped the boiler and we put in silica sand again, and quite rapid you can see that we had the same behavior again. So one of the things could be that we actually take up the ashes inside the particles. Another thing could also be that you have a more smooth temperature profile in the furnace due to the oxygen transport, which then gives less locally high temperatures, which can melt ashes that will end up on the heat transferring surfaces. So something about the increased oxygen distribution. We made a small test in the Chalmers boiler where we actually fed in fuel as a pulse into the system. And then we measured the oxygen in the dry flue gases, and we measured the carbon dioxide in the flue gases at the same time. So what we did was that we threw in a bucket of fuel corresponding to 9 times the actual load in the boiler. And you could see that the oxygen concentration in the flue gases goes down, and there is a CO peak because there is not enough oxygen present. And this was carried on for more times, and all the time you could see the decrease in oxygen. When you stop the boiler and have ilmenite operation instead, you could see a different thing, and it's that actually the same pattern was with the oxygen concentration. The oxygen concentration goes down in the gaseous phase, but there is never any CO. There is some CO, but there is very little CO compared to the silica case. And this is due to that you actually have oxygen stored in the bed material that is already present in the furnace, more or less everywhere in the furnace. So the gaseous CO and other fuel is actually reacting with the bed material to form CO2 and water. We also tried this in the Chalmers boiler, where we put a gas probe into the furnace, where we put the probe roughly 5 millimeters from the membrane wall inside the furnace, just to see how the CO profile looked very close to the wall. And what we could see was that when we operate with silica sand, we got a certain concentration of CO at 3 different points at the center wall, front wall, where we have the fuel feeding, and the center and the back wall. And compared to when we stopped the boiler and operated with Improbed, there was a drastically reduction of CO close to the wall, meaning that there will be more oxygen present close to the wall when you use this Improbed instead. This was in pilot scale. Now we tried to also do this in large scale. So we did it in one of the municipal solid waste fired boilers at Händelö. And you can see from those 2 figures that it's the same thing. You have the oxygen concentration on this axis, you have the carbon monoxide concentration on this axis. This boiler is already operated with a quite high oxygen concentration. This is dry flue gas, but still is quite high. You can see on the daily operation, there is a lot of CO peaks. And you can see that the system is quite sensitive, and there's a lot of changes in oxygen as well. This is due to the fuel. Municipal solid waste is an extremely heterogeneous fuel, and it's hard to get fed in a proper way. So, but we then started to feed oxygen carrier instead, and this improbed. And you could see that after some days, when you have started to build up a concentration of this bed material, you could actually reduce the oxygen quite a lot, from roughly 7 something to below 6. So an O2 reduction about 20%. And you could also see that there was a daily decrease of CO by 50%. Of course, there could be better fuel. Sometimes we can see changes all the time, but I think that as this was operated for almost 200 hours, you could definitely see that there is some kind of change. Another more interesting thing is that we could also reduce the amount of bed material from 11 kilograms per megawatt hour to 3 kilograms per megawatt hour in this boiler. So how much silica sand is used is very much dependent upon the actual boiler, but 11 is quite a lot. It should be more like 6 kilograms, I would say. What we also saw is that if we could increase the ilmenite concentrations even further, it would be beneficial for further optimization of this system. Another example is from a boiler in Örtofta, Sweden. It's a 115 megawatt waste and biomass-fired boiler. In this case, we also followed the bed material from the point of how much of the bed material in the boiler was magnetic. So we simply removed bed material from the boiler each day, and then we used a magnetic separator to get out the particles. So we could follow the concentration profile in the furnace of using this equipment and how much of the improbed material actually was inside the furnace. So you could see that as much, there was like 90% of the bed was magnetic, meaning that it was improbed. And you can also see that we tried different amounts of feeding to the system. And at some case, we put in silica sand, and you can see a drastic reduction of the improbed in the system. So what could we see from this? In this case, we could see that we could actually increase the boiler load from 115 to 123 megawatts. And why could we do this? Yeah, because we could reduce the O2 into the boiler. We can reduce the surplus of oxygen. And this is due to that you can distribute the oxygen in a more proper way. So this line is symbolizing the oxygen concentration when you operate with silica sand. And this is the ordinary effect that you have on the boiler. So you can see that it was actually changed from roughly 2.5% to below 2% in the best cases. You can also see that we increased the boiler load by 8 megawatts, which actually is a 77% increase. This has never been done before in this boiler. This is also an effect you can see that you actually reduce the amount of oxygen into the system or air. Is that with silica sand, you can see that you have, if you sum up all the gases, the primary air, secondary air, and you also sum up the recirculated flue gases, you will have a certain amount of gas all the time. But as you remove air, you can also reduce the recirculation of the flue gases. As this material is less prone to agglomerate, you could actually have less flue gases out from the system. And this, of course, gives you the ability to increase the fuel load, as you will not increase the velocity of the flue gases that could affect the convection path. But, of course, this is only possible if the boiler is possible to increase the load. So you need to have a steam system which can allow for a higher increase in fuel load. One proposal to actually improve the fluidized bed combustion, when you actually from the beginning, if you just have a fluidized bed combustor, you would simply remove the ashes. The first case to improve the ash handling is to put on some kind of separation and recycling of the bed material. So you could have a mechanical separation by a mechanical sieve, We take out coarse particles, but you can then transport back fine particles again. This could also be a classifier where you use air instead of a mechanical sieve. So in that sense, you will have more or less an extra fluidized bed, putting back the fine materials and then leaving the coarse particles to leave the system. Another way would be to also introduce a magnetic separator in this. So basically, you will have oxygen carriers. In our case, as I said before, we have been working with ilmenite and improbed. So what you do is that you simply take out the bottom ash stream. You will run it through a separator. You will have out the coarse particles, but all the other particles will go over a magnetic separator. And the magnetic particles, meaning mostly the ilmenite and the improbed, will then be transported back again to the furnace. So in that sense, you will have a recycling of the particles. And the particles which are not magnetic attracted will simply be sent to the bottom ash system. And this will also include ash and spent oxygen carriers. This system has been implemented now in one of our facilities in Sweden, the 75 megawatt municipal solid fired CFB boiler. And with this, we could see that we could actually reduce the total amount of fresh bed material from 11 to 0.8 kilogram per megawatt hour. However, there are some experience and some issues with this. We've learned that municipal solid waste is quite tough fuel. You can see all the metal threads that comes in with the fuel. They get stuck sometimes in the sieving equipment. So this is now rebuilt to have a more robust system, but the magnetic separator works actually properly as it should. So this is something that is now rebuilt. There is also another twist on active bed materials, and as Bo was mentioning before about the chemical looping combustion, and we also heard about oxyfuel combustion in fluidized beds. This has been done a lot in research scale, especially chemical looping combustion in research scale. We think that what you actually can do is that you could use those experiments done now in large scale, because we have tested different oxygen carriers. We have learned much more about lifetime. And also, not to forget actually, which you'd never really see in those lab scale experiments, is the ash interaction that appears with oxygen carriers. And also boiler performance on how this works. So we believe that this can actually motivate the learnings more about oxygen carriers and what kind of technology you choose with the fluidized beds. The oxygen carrier could actually make a great effect. And one of the motives is that, I mean, you could benefit already from using this OCAC concept, because you could get all those things like increased efficiency and less agglomeration, for example, if you have issues with that.
Mr. Lee, can you unmute yourself? Mr. Frederick, can you unmute yourself? Yeah.
Sorry, can you hear me now?
Yes, yes, yeah.
I don't know why it muted itself.
Yeah.
Okay, so to sum up, as I said, we need to learn more about this system, how to recycle the bed particles, because it's still more expensive than silica sand, but we can see that there are great benefits from using this bed material. So I think that I will stop there. Thank you for listening.
Thank you so much, Mr. Lind, for providing us information about active bed materials. So now our next speaker is from Thyssen Group India, Mr. T. Prasad. We're going to talk about Thyssen CFB technologies from Thyssen. So Mr. Prasad, if you can share your screen.
Yes. Hello everyone. Is my screen
Okay,
visible
thank you.
to all of you?
Yes.
Okay, thank you. See, we have 4 divisions actually. We have sugar manufacturing plants. We have boilers. Then we have mining equipments. We have cement manufacturing. Then we do O&M services for all the power plants as well as the material handling systems. And we have 2 works, one in Pune, close to Bombay, and one more in central India, at Hyderabad. We are committed to the environment. We make fluidized bed boilers, also cement waste heat recovery plants, steel plant waste heat recovery plants, biomass fed boilers, to name a few. These are the offerings what we have. We have reheat in the range of 300 megawatt, 300 tons per hour up to 1000 tons per hour. We have non-reheat up to 500 tons per hour designs available. We have vast experience with bituminous coals, as well as petroleum coke, lignite, and also to some extent on biomass firing. We did experience hydrogen firing.
Mr. Prasad, you're muted. Could you please unmute yourself?
Yeah, am I audible now?
Yeah.
Okay, I'm sorry. So we have a technology which is quite different from the rest of the world. We have complete heat transfer surfaces in the first pass. Our cyclones work at a temperature in the range of 400 to 450 degrees Celsius, and then the ashes are recycled back. So we call it as a cold ash recirculation. Then we have no bed material replenishment which is required, and what are the fuels we have experienced. We have effective in situ desulfurization and very good control in reducing the NOx emissions. We have no soot blowing equipments. We don't need any oil to support at pat loads or low load operations. Since we have very thin refractory onto the membrane walls, our startup times are much quicker, and we have demonstrated a very good availability on most of our units. We have exclusively improvised on the design of the nozzles, which is creating very effective fluidization, and it's a tower type design. And normally we have seen that spares are not any special spares are required for our units. We have a footprint at home of about 75 plus units across India, firing various fuels right from low ash, right from 4% to very high ash up to 60-65%, which is designated as washery rejects on coal washeries. We have also units with sulfur content right from decimals up to 8%, which is petroleum coke. We have also units working with low moisture fuels as low as 4 to 5% and as high as 40% moisture coals, which are called lignites. Across the globe, outside India, we have 6 references, 1 in UAE, 2 in Indonesia, and 3 in Philippines. Coming to clean coal technologies, there are pre-combustion cleaning, which is designated as beneficiation or washing or coal drying. Then all our, the gentlemen before me have already explained, there is one gasification which can be on fluidized bed. Then one route is fluidized bed combustion, which is CFB. And the fourth route is post-treatment after the combustion as gas cleaning technology. Coming to CFB, biomass can be used as alternate fuel apart from coal as co-firing. This has already been displayed by all our colleagues, right from Dr. Saraswat. The way you take a left from the right of 10 degree to 0, you find the difficult fuels which are difficult to burn, needs careful analysis and design of the boiler to provide proper availability, proper combustion, and even the emissions that are to be taken care. And these are all more challenging. We have also seen that the alkalis will play a very big role by way of bed agglomeration, fouling, emissions, furnace corrosion, and also pose problems to ash handling as well as the emissions on the systems. We have experienced some of the biomasses which are listed here in some of our units. We have experienced rice husk with co-firing in our CFB. They have fired up to 10 to 12% in existing unit having coal. And another unit we have seen the RDF. They have the plastic powder which they have got it from outside and they have tried it, something very close to 15 to 20% again. And also in one of the units we have seen the camel dung, which is having good calorific value. They have tested and they have fired more than 20%. So these are some of the experiences we have. Apart from that, we have one of the gram dal stem, which is like paddy straw, you can say. So the stem also they tried to a small extent, but they found that it is going and sitting on the heating surfaces. So they have discontinued that. So these are some of the experiences we have seen in our existing installations. But we found that most of the time these are comfortable on an existing installation with properly giving the steam temperatures, pressures, what the CFB has been designed with coal. So co-firing to an extent of 10 to 12% is comfortably possible in any CFB in an existing unit. The only problem which poses is the upstream handling system. So based on that, if it is taken care, small percentage of this in an existing unit is absolutely possible. These are some of the benefits which already my previous speakers have explained. The CO2 emissions will be much lower because these biomass fuels are CO2 neutral. SOx emissions also will be lower because the biomass contains less quantity of sulfur. The NOx emissions will be lower in a similar tune to the content of nitrogen in the fuel. The dust emissions also will be lower and there will be conservation of fuel. Also, you can see there will be a better environment which can be thrown for the Indian market. Now coming to oxy-fuel combustion again. In this process again, the pure oxygen instead of air as the primary oxidant can be used, and nitrogen, if it is removed from the input air, to an extent of 95% of oxygen can be made available for firing into the boiler. But the flue gas recirculation is definitely required because when we see the N2 and O2 between in the air, the ratio it is 77 to 23%. So the moment we remove nitrogen from the air, so the oxygen straight away will reduce the flue gas quantity to very low, which sometimes will pose problems for the fluidization. So in an existing unit, it will be difficult to try this fuel as it will pose a lot of problems on the operation and it may seize the fluidization pattern in the system. Whereas by employing the flue gas recirculation, it will increase the CO2 level in the flue gases. We made a small thermal calculation, you can see on the right side in the table. When you have only air firing assisting the combustion and we have oxygen assisting the combustion, the CO2 levels and SO2 levels will be increasing quite high. So the picture again, which has already been displayed by most of the delegates, the air is separated, the air separation unit, and then the oxygen is supplied. After the flue gas cleaning, it can be tapped, or after condensing the water content in the flue gases, it can be tapped and recycled back. The recirculation is basically provided to assist. One is the temperature control, second is the velocities which are required to maintain in a CFB. After the subsequent system, the CO2 can be compressed and it can be used further transported from the system. Another clean cooling technology could be cold drying as a pre-combustion cleanup. So cold drying will have some of the benefits that you find out that in the drying operation, the surface moisture can be very effectively separated by the evaporation process. Lignites and subbituminous coals are mostly attractive for the power plants, what we observed in India, due to their low cost and the emissions. However, these contain high amount of moisture as well as ash. So when these coals are burned, the evaporation losses will be to the tune of 5 to 7% in case of lignites, high moisture fuels, 2 to 3% in case of coals. So this result in very high fuel flow, higher stack flue gas flow, and lower plant efficiency and higher maintenance cost compared to low moist coals. So on the right side, you can see what are the various advantages for cold drying. This helps in burn cleaner and more efficiently the fuel. Coal heating value will increase, thus increasing the boiler thermal efficiency. The flue gas flow rate will be reduced. There will be increased life for the boiler internals. Also, the exhaust waste heat recovery is also indirectly attended by from the gases which are getting out from the chimney. This is a small pictorial view of representing cold drying facility. You can have the drying in a cold dryer. It can be a flash dryer or a fluid bed dryer or a different kind of a dryer which is available in the market. Then those drying, if you can provide the hot air from the system by exchanging indirectly the flue gases coming from the chimney, and then that hot air, if you can introduce it through the dryer and then take it out, then we are able to conserve the volatiles which are there in the fuel, and then the system can be employed. So this way the cold drying is one methodology that can be adopted to have a clean combustion. We are developing a small pilot plant. It is at the engineering stage where we would like to test various fuels to understand the combustion characteristics of the various fuels, to understand the fouling phenomena, to assess the emissions getting out of the unit, and various fuels including biomass can be tested in this. Even the oxy-fuel combustion can be simulated in this, and based on that, what all modifications that are required to be suggested to design the boiler, to alter the boiler, and go further on the system can be thought of. So we have under the engineering stage at the moment for this, and we are looking for investors towards building of this system. This is a 5 megawatt thermal heat duty based system we want to put in place, and there are no superheaters and evaporators and drum in the circuit. We want to only heat the water and then cool it back and then recycle back, so that our aim is to see how is the combustion characteristics happening in the system, fouling and gas emissions that are happening through the circuit. So in this, whatever fuel is there, whatever fuel is available, whatever fuel one would like to burn and test it and check it, this facility will assist in doing that. So this is what we are planning to develop and see, and then that's all from my side after the pilot plant, and we are looking for investors, as I told you. So that will help us in building this. We have land available in one of the factories of our premises. So this is one thing which will help us in understanding and then building it. That's all from my side. Thank you so much for the patient hearing and small presentation from my side.
Okay, thank you, Mr. Prasad, for providing us Thyssen Group's perspective. Our next speaker is Mr. Frank Luschke from Dushan Lenche. He'll be talking about CFB technology for the 21st century. So, Mr. Frank, you can share your screen.
Yes, I'm just starting it. Hope you can see it.
Yes, Mr. Luschke.
Yes, you can see.
Yeah.
Okay. So thanks for providing me the chance to talk, and I'm quite happy to talk in between Mr. Prasad and Mr. Lakshmi Rashiman from BHL, because both of them I know quite well and have worked together with them some 10, 20 years ago in the history. So I will provide you some information about Doosan and the CFP technology from our company. Hope you can see the second file which I have opened right now. This is the content I want to touch today, truly quite briefly, because half an hour is not so much time. I will give you a very short overview about the CFP history and the basics of the CFP. I guess we can already skip because it has been explained several times today, and most of you definitely know quite well anyway. I will give you some ideas about the fuel flexibility and the range of fuels which can be burned, the advantage of co-firing coal and biomass, also the possibility of converting existing plants from coal to biomass. Also heard several times, so I will also shorten this definitely, is the design challenges when firing biomass. Maybe more important than in my presentation, I will put a spot on the efficiency, the steam parameters which are required for that, and the CO2 footprint from such plants. And then I will finish my presentation with large-scale CFBs with USC steam conditions, as well as some spotlight on emission control and the future outlook. So very brief about my company. I'm part of the Lenches, which is a German company.
It's not moving, Mr. Luschke.
It's not possible to see your presentation.
Why not?
We have the pleasure of seeing you, but not the presentation.
That's what I don't want to show you. Let me just see. So, can you see that? Just a second. So, can you see it now?
No,
okay.
Yes.
Okay, great. So sorry for that. I'm working here with 3 different screens, so it's not so easy to see which screen is on the presentation. Okay, so as I said, not too much to my company. I'm part of the Doosan Group, a German company called Lenches, and we have been taken over by Doosan some almost 10 years ago. As you can see, we are part of the so-called power service group within the Doosan, and there are some more European companies like Doosan Babcock in UK and Skoda Power providing turbines. But I guess this is not what you are so much interested. So maybe I can show this. And thanks to Professor Bo Leckner, he has helped me to develop this diagram some further. It looks quite complicated, but what I want to show is quite easy. I hope you can see my mouse. Can you see that?
Yes.
Okay, so it all started back in 1976 when when a German company called Logi in this time placed a patent for the CFP technology, and thanks to, let's say, the very good people doing this, they covered a lot of the basics which are still valid today on CFB. So due to this, and this should be demonstrated by the blue lines, many companies, specifically boiler manufacturers, took license from Logi at the beginning to use the CFP technology. You see all those lines, and you see the boxes with the different companies available in the CFP market over some time. On the left axis, you see the years. So as I said, it started in 1976, and you can see further down, just concentrating on my own company. As I said, Logi put a patent, And then there was a joint venture, which is this green box between Deutsche Babcock and Logi. Logi was basically a chemical company and an engineering company, while Deutsche Babcock was a boiler manufacturer. They worked together. Also, Lentjes joined. There was a company founded then, which was called LAB, Logi Lentjes Babcock, which also gave licenses to different partners in India. We had some renaming, some taking over from other companies. Just coming to where we are today, we have been taken over in 2011 by a Korean company called Doosan, and the new company name now is Doosan Lentjes GmbH. And we are still offering, let's say, the original CFB technology, which has been developed by Logi some more than 40 years ago right now. Also very brief, as I said, it was developed and the first patent was given in 1976. So in 2016, we had 40 years of CFB and we had a celebration, our company. And you see the three nice guys here, all of them professors, and I'm sure Bo Leckner knows all of them. They have been the original founders of the CFB patent and they are still alive. Hope they will have some more years. And they were very interested when we had a small celebration of 40 years of CFB in our company. So this one I will skip because I'm sure all of you know already. It just demonstrates the differences between a bubbling fluidized bed, a CFB system, and a transport reactor, which is basically similar to a PC-fired boiler. So what is the difference between PC-fired boilers and CFB? It's quite easy to explain. On CFB, we can control the emissions by controlling the properties of the combustion process. That means by controlling the temperature, the air, and limestone addition, we can control the emissions to limits which today are valid all over the world. If you have to do the same in a PC-fired boiler, and this is also nothing new to India, you have to add flue gas desulfurization and SCR units. And the experience in Europe was, and this most of my colleagues who have already presented will confirm this, once we had strong emission limits in Europe, but basically the boilers which have been built after that have been typically only CFB boilers so far. The capacity which was required by the client was available at that time. Okay, this I will skip. This is how a CFB boiler works. Also nothing special. We have discussed this several times today, so I hope I can save some of yours and my time. Also, this we have seen several times today. So this is how we show how the different fuels look like, which can be burned in a CFB boiler. On the left axis, you can see the heat value of the fuels. On the bottom axis, you can see the sum of the ash and the moisture, which typically is inert and cannot be burned. And surely when increasing ash and moisture, the heat value goes down. And those, let's say, edges demonstrate the typical fuels which are available on the market. It has been demonstrated by our CFBs as well as by all of the competitors that all these fuels can be burned very satisfactorily in a CFB boiler. Also, it was mentioned today in one of the presentations that due to the higher oxygen content in the biomasses, for example, even though they have a very low ash content, the heating value is comparatively lower than on the old fuels like coal and lignite. Also, this we have seen today, it looks a little bit different than most of the others have shown, but the information behind this is the same. We do have so-called standard fuels where we know very exactly how a CFB plant should look like. And this is what we call so-called standard design for bituminous coals, for hard coal, for pet coke, anthracite, some portion of the brown coals. We do have very difficult fuels which need a very specific design and which provide specific design challenges. And this is typically waste wood. As you can see this picture here, for example, this is very common in Europe right now. It's called waste wood. It's called biomass combustion even. Basically, it's waste which contains wood. But it sounds much better if you say we have a biomass combustion. Nevertheless, because of all the ingredients in this kind of fuels, like painting, like heavy metals, maybe also some screws and nuts and whatever, you have to take specific precautions in the design of your CFB to operate it very sufficiently. And the same is also valid for some portion of the biomasses, as you can see here. So why all these efforts on biomass? This was also discussed on the left diagram. You can see the different fuels, solid fuels available on the market today. So the left side shows the fuels which have been stored since millions of years and have stored the CO2 which they have taken out of the atmosphere. And on the right side you see the fresh wood, which is the which takes out the CO2 of the atmosphere right now. And this is how biomass combustion is counted. If we take fresh wood and it takes the CO2 of the atmosphere today and we burn it tomorrow, it's counted as CO2 free. Why, in comparison, if we take one of the other fuels, including peat, which have been stored since at least thousands of years or millions of years, we add CO2 in the atmosphere, which we don't like. And this is what you can see in the other diagram, also nothing new. Everybody of us knows already. Since humans are burning a lot of this stored carbon, we have a very drastic increase of CO2, and we're just starting to learn what happens with the high increase of CO2 in our atmosphere. And definitely we have to do something against this very, very soon. Therefore, this is a comparison now. Let's say example calculation, what we have done. We have taken a 300 megawatt CFB power plant, and we have compared two things. We have compared a so-called subcritical lignite-fired plant, which provides an efficiency of, let's say, 37%, compared with a supercritical coal-fired plant, which provides a plant efficiency of 43, maybe 44%. So you can see in the left diagram what happens with the CO2 emissions. So if we take this lignite plant, we will produce around 1,100 grams per kilowatt hour. Once, if we have already a supercritical plant and coal, which has less of moisture, then we will produce only 800 grams per kilowatt hour approximately. And now we come to the case of co-combustion, also discussed several times today. So for example, then if we add 20% of biomass instead of these coals, then we can come down with a subcritical lignite plant from 1100 to about 880 grams per kilowatt hour. And if we do the same in the supercritical coal-fired plant, we can even come down to 640. And if adding more and more biomass, surely you can see this effect. I was asked sometimes when I presented this diagram, is it really zero if we add 100% of biomass? Basically, surely this question is correct, because we do need transport of the biomass, which today typically is done by trucks or by ships, which surely still produce some CO2 for the transport. Surely this is not included in the calculation. And by the way, also the extraction from coal from the earth also produces additional CO2, which is not taken part in this calculation. One important issue, which interestingly was not touched today, due to the low heating value of biomass, typically, you can see it's less than half of compared with typical coals, or still much less compared with lignite. And also due to the different density, typically for the biomass. Some issue is quite important. If we want to add biomass instead of coal, or even convert a plant to 100% of biomass, due to the lower heating value and in parallel the lower density, we need much more storage space for the biomass as we have used before for the coal. And this is what this diagram should show. It shows the tons of fuel per hour. So coming to the lignite for this example for 300 megawatt subcritical, we would need about 180 tons per hour of lignite. And if we add 20% of biomass, we would still need 145 tons of lignite. But at the same time, we would need 55 tons additionally of biomass. Again, looking at the lower density, surely we need much more storage space for this. And this is at least important for people thinking about adding biomass and doing co-firing. They have to keep this in mind. This was also explained today several times. So this is typical properties of different biomasses available. Also said several times, in case of burning biomass, we have to be aware about agglomeration, fouling, and corrosion, which is much more critical in case of biomass than it is with usual coals. But one thing which, from my point of view, was also not addressed sufficiently today was that if we look at the different biomasses, they also can change their properties very, very hugely. For example, if we take olive waste, it can contain chlorine from 0.2, which is already high, up to 0.5%. And kalium, which is, as we learned also today, responsible for agglomeration from 5 to 30 grams per kilogram. And this is very well the same for many of the other biomasses. So when designing a plant for biomass combustion, we should know the properties, and we even should know the ranges of the fuel which is expected for the next 15, 20, maybe 30 years of operation to design the plant exactly to the demand which is required. And another example is straw, for example. For straw, it's very important where it comes from. So it can have a very wide range on the different properties, as you can see, just depending if it is growing close to the seashore or if it is growing in the middle of the land or whatever other reasons are related to this. So you cannot just say, I want to burn straw and just design me a plant for that straw. We need a little bit more of the details, what kind of straw you want to burn, where it comes from, and especially the chemical composition, including the ranges of these fuels you want to burn. So corrosion, as I said, is one typical risk for biomass combustion. There are two typical corrosion risks in a boiler, not only CFB boiler, but in every kind of boiler. One is the so-called cold and low temperature corrosion. This is typically related to the SO2, SO3 in the flue gas. And this is what we quite well know from the cold combustion. And this is related, let's say, to the design of the air preheater and the economizer and the flue gas exit temperature, what we have to design for a boiler. More critical is the so-called high temperature chlorine corrosion, which is related to the chlorine content in the fuel, which comes up at about 450 degrees C, you can see, and it's drastically increasing with the temperature. And I have to say, important is this temperature is not the flue gas temperature, it's the surface temperature of the tubes. So this temperature is not only related to the flue gas temperature and to the chlorine content, it's also related to the steam parameters. Surely understanding if I have a higher temperature in the tubes inside, then also the metal temperature on the surface will be higher. One issue which is very important to learn, especially for co-combustion, I will come to this later in more detail, but we also noted that if we have a so-called sulfur to chlorine ratio of, let's say, 4 and more, typically we do not have a real problem with the chlorine corrosion. This chlorine corrosion, definitely we will have a problem if the sulfur to chlorine content is much lower than 2. And this is the reason, by the way, that in a pure biomass combustion, we do not do any desulfurization in the combustion process anymore, because as seen before, biomass contains already lower sulfur content, and we are, let's say, under those conditions for pure biomass combustion, quite happy to have at least some sulfur in the flue gas to reduce the chlorine corrosion risk. I will not go too much into detail on the corrosion mechanism and the prevention of this, because there is several literature available in the internet, and everybody who wants to look into those details can very detailedly check all these things. But it's quite important to know, and this was said already several times, that the alkali and especially the chlorine content plays a very important role for all this. And as I said before, if we want to design a CFB boiler for the specific fuel, we need to know what is in the fuel and what is expected in the fuel in the future. So just to sum up, these parameters play an important role in the corrosion issue. This is, as I said, the tube surface temperature, and this is determined by the flue gas temperature and by the fluid temperature inside the pipe. In addition, surely the chlorine content in the flue gas and its species is very important. As I said before, also the sulfur content in the flue gas, in this case, a higher sulfur content is better than a lower sulfur content, plays a role. The alkalis and related chlorides are important for the mechanism which is behind the corrosion issue, and also the O2 content in the flue gas by oxidizing or reducing atmosphere plays an important role for the different ways of corrosion mechanism. Also, the thermal gradient in the deposits plays a role, and finally, surely the flue gas velocity. This was also said in one of the previous presentations, that typically corrosion and erosion always play hand in hand, and tubes which are already affected by corrosion will be then finally destroyed by erosion or opposite. So this is something, again, specifically for CFB, which has to be taken into account. I will just show one reference today, because this is a very interesting reference. This is our plant in Berlin, in the German capital. This plant was commissioned back in 1989, and this plant was designed, you see the same diagram as we had before, specifically for hard coal and for the addition of a very few portion of lignite, possibly. And so just a short history. So we got the contract back in 1986. When the boiler was commissioned, it was the largest CFB in Europe, as I said, designed for hard coal and lignite, nothing else. It was operated till 2004 on Polish and German hard coals with a quite low ash content. In 2006, after 16 years of operation, they had the first overhaul of the turbine, and they changed the operation to Polish hard coal with a higher ash content, which could be also noted in slightly higher erosion effects on the existing boiler. Then in Europe, the discussion started about CO2 and more cleaner flue gas and less flue gas. So the operators were, let's say, forced to think about what to do with the existing boiler, already 20 years old. The decision was then in 2011 to add biomass, and this is why it is the example here. On an existing boiler never designed for biomass, the operator decided to operate in future on co-firing biomass with a coal. So they added the first system for biomass, which uses fresh wood collected around 150 kilometers around the German capital. And the capacity for this system was up to 50 cubic meters per hour. With this system, they could add 10% of the thermal capacity, and as shown before, accordingly reduce the CO2 footprint of the plant. Then the discussion went on and on. So there was a second decision in 2014. They commissioned a second biomass system, this time with a capacity up to 160 cubic meters per hour. Which provided additionally 40% of the thermal capacity, which means now both systems together, the plant today can operate on 50% of biomass, and it operates still very successfully without any problems. And I still have to say the plant was not designed for biomass. This is something which is quite important. And just going back to the first picture, the plant was already designed, I forgot to say this, for 196 bars. So this is a pressure which is very close to, it's already one through pressure, and this plant already uses a pump, even though the steam temperature is not super critical, but the pressure is already high. And this means that we already have still high surface temperatures on the tubes. Even though with 50% of biomass, the plant still today operates very sufficiently. And there is a future discussion ongoing to convert this plant even to 100% of biomass. So what has driven the operator to this decision? So they had an existing 20 years old boiler. This boiler was designed for combined heat and power. This is also very important if we talk about efficiency, because under those conditions, at least in wintertime in Europe, when it is quite cold in Germany, they provide a lot of district heating to the surrounding living areas of the people. And that means under those conditions, the plant operates at an efficiency of 85%, which is, I guess, almost unbeatable. Then, as I said, there was a decision to substitute about 50% of the combustion heat by wood. Okay, so what they had to do is they had to look for the available biomass around the Berlin city, not to have too much of transport capacity. And as realization, and this was also what I explained at the beginning, because of the lower heating value of the biomass combined with the lower density, they needed additional storage at site of 9,000 cubic meters for this additional biomass. So just some few pictures, what was added. The white tall building here in the background is the CFB boiler, and this is the turbine hall, and behind that is the ESP. So they had added, this was the first system, a 10% biomass supplied by trucks, what you can see here in the bottom, and then feed it directly into the combustion system. And when they decided to increase the capacity, they have added a ship unloading. Fortunately, the plant is on a channel, so they could use this transport ways by ship. And they have used an old existing turbine hall, which was not in operation anymore. And this was converted to the biomass storage. Quite interesting solution, but there was no other space inside. And just by the way, just compare. This left side picture is the original control room as it was commissioned in '85. And when doing all these changes on the plant, they have also stepped into a new DCS system and a modern system with a screen control. And this is the control room as it looks today. So discussing what fuels are possible, what are the alternative fuels of co-firing in CFB. On the left side, we have the, let's say, more conventional fuels, which is bark, biomass, wood pellets, and so on. And on the right side, we have the more difficult fuels, which is packing materials, pipe sludge, RDF, seawater sludge, and so on. So all this can be co-fired in CFB. But as I said, surely once you have a CFB in the existing one, and you want to burn the one or the other material in a certain portion, you should talk to your supplier and discuss what you want to burn and how you want to burn and how much. And then definitely, I'm sure with existing CFBs, with almost all of them, there is a solution what to do. So coming to, let's say, this is my personal expectation, what is the advantage of co-combustion? And this I would just take in comparison to biomass-only combustion. So if we do co-combustion, we can use the advantage of the higher efficiency due to larger boilers and the higher steam parameters, which are typical with larger boilers. So even if we go up to USC conditions with 620 degrees C and 280 bars, which is state of the art today for PC as well as for CFB, then we can gain from the high efficiency of 44–45% of these high steam parameters, but still not having the risk of the biomasses with agglomeration, fouling, and corrosion, which will happen in case we have to burn 100% of biomass. So this, from my point of view, is a quite important figure. Also with the coal ash, and this is specifically valid for India with high ashes, we do still not need any sand addition for the biomass. So you can even reduce the ash content for the ash extraction, save some money on this, and still do not need sand addition, which was also presented in one of the before presentations, that in case of 100% biomass, you have to add something, sand or even more advanced materials to keep the fluidization process and the CFB system running. The other advantage is if we have still coal and coal ashes in the plant, we do have the dilution of the alkali and content of the biomass. And this means, as I said before, there is less or even no risk of fouling still, so long we have not too high portions of biomass. This was also explained, the high sulfur to chlorine ratio, which is usually given whenever burning a certain amount of coal, reduces or even deletes the risk of chlorine corrosion. As I said before, you have a reduced ash discharge and less limestone consumption. So let's say, looking at this, in case you want to build a 600 megawatt CFB plant and you add only 10% of biomass, which is 60 megawatt, you have the same effect on the CO2 emission as building a 60 megawatt biomass only plant. But I'm sure the risk and the problems you might have in the operation are much lower and much more controlled compared to a 60 megawatt biomass plant only. So long the, let's say, political situation accepts co-combustion, I would prefer the co-combustion, especially with look on the economics of this. This is also a diagram we have seen, maybe not exactly the same, but quite similar before. On the left axis is the plant efficiency you can reach. On the bottom axis, we have the increase of the steam temperatures, and you can see the different types of combustion: grade firing, BFB, multi-fuel CFBs, subcritical CFBs, supercritical CFBs, and PC, and so on. You can see the possible increase of the plant efficiency, and this surely is related to the reduction of CO2. And as I said, if you would have the advantage to even use some heat, as we can do it at least in the cold countries like Finland, Germany, Sweden, for district heating, then you can raise your fuel efficiency up to 80% or even higher. So another example, this is a plant we are right now building in Japan, also very briefly. It's a 75 megawatt biomass only CFB. And with this plant, we can reach a gross efficiency of about 42%, even though quite high. If you look at the steam parameters, it's not USC, but it's the maximum you can do with a drum type boiler, which has around 560 degrees C and 170 bars, and truly it's a reheat system. If accepting biomass for this kind of steam temperatures and steam parameters, we have to limit the chlorine content as well as the alkali content in the ashes to certain amounts. And this is what I said before. We as a designer, and this is valid for us, for Foster Wheeler, for ThyssenKrupp, for BHEL, for all the others on the market, we need to know exactly what will be the fuels you want to burn. And then we only then we can decide what will be the steam parameters we can offer you for this kind of fuels. And looking back to the picture before, if we then decide to reduce steam parameters because your fuel may contain more chlorine and more alkali as we would accept, then surely the plant efficiency will drop accordingly. These are some pictures from the workshop from the plant, which is in construction right now and will go in operation next year. So this is a modern biomass CFB plant concept as we would offer it right now. And this is, let's say, based on the markets like Japan or Germany or Europe, where we have in addition, very high requirements on the emission limits. So it's a so-called integrated design what we offer. You can see here very briefly the entire combustion chamber in green, the cyclone and the recirculation part. All this is of membrane wall type. All this is exactly in the evaporation temperature loop. And that means that all the expansion joints which have been there earlier in the CFB could be removed or are comparatively small. Also, this was always a discussion and a problem in the older CFB design, that with the expansion joints there have been problems, so they have been almost removed in this kind of systems. Also, the cyclone is a water tube type, which means instead of having 30, 40 centimeters of refractory, we talk about millimeters now, which is just an erosion protection, no heat protection anymore. So it's a so-called steam-cooled cyclone in this case. You can see this is a modular system. So in case the NOx emissions are quite low, as they are, for example, required in Japan, we could add an SCR system, but this is just in case it's required. Usually with our CFB combustion and, let's say, optimized air addition, we can reach the typical limits on NOx without an SCR system. In addition, we could also have a so-called bicarbonate injection before the backhouse filter, which would help to reduce all sour gases. So not only SO2, SO3, also chlorine, HCl, for example. So these are the concepts we are offering today on the market. So we have so-called one cyclone design, which is typically, which we can use up to, let's say, about 80 megawatt electric. We have a two cyclone design, which we can use for up to 150, depending on the moisture content of the fuel, maybe up to 200 megawatt electric. We do have a four cyclone design, 4 in a row, which provides around 300 megawatt electric, typically on subcritical conditions. And we do have our supercritical, ultra supercritical designs for the large scale for 300 or even for 600 megawatt electric available. And as I said, in such a boiler to add 10% or 15% of biomass could just delete the use of this kind of boiler on the pure biomass basis. So ultra supercritical CFB, just a few facts how this looks like. So the unit size, what we have designed, is typically up to 600 megawatt gross, can be more or less, but this has turned out to be a quite economical size. We use 6 cyclones in this case. In this case, it was designed for Indonesian fuel, which is easily available on the market with the steam parameters of 610 and 620 for the final superheated steam and the reheat steam, and the steam pressure of about 280 bars. With these conditions, we reach SO2 limits of less than 50 ppm, NOx also less than 50 ppm, and the dust even lower than 15 ppm. A comparison of 600 megawatt CFB and a PC boiler, you can see that even the footprint, and not the CO2 footprint in this case, but the size of the plant is lower in case of a CFB unit, and this adds to the point that in case of a PC boiler, you even would need still what was explained in the very beginning of my presentation, you would need additionally FGD and additionally SCR. And you have to keep in mind these additional systems, FGD and SCR, are additional plants. So they also require maintenance, they require service. They can even be a reason for a shutdown of your plant because of some problems. So they would also limit your availability. So if I would have to go for a 600 megawatt unit today, under the given emission limits, and even under the chance of using the flexibility of a CFB system, I would always go to a CFB system. Due to the fact that we are today talking on, let's say, more with university also, I also want to show what we have learned. Sorry to interrupt, Mr. Frank.
How long this might take? Can we conclude it in another 5 minutes?
I guess 5 minutes, not longer than this. I'm almost close to the end.
Okay, great. Thank you so much.
Okay, so just very briefly. So what we are doing today, and this is very different than when I started my career back almost more than 30 years ago, when I wanted to know what happens in a cyclone. I had to put my hands on the cyclone and try to find out what is inside. Today we have very nice tools where we can do CFD simulations, and this is just an example to see what we can do. You see the particular volume fractions, what we calculate, and you can see the temperature regime over the height and different levels of the boiler. And this is quite important for good carbon burnout as well as for lowest possible emissions, that we have a very good temperature control and temperature profile over the boiler. So another example, and this is what we can do today with CFB before building the real plant, and this we do typically on all our designs. On the left side, we see a starting point of a 600 megawatt CFB USC, and on the right side, you see what we have learned doing the CFD and they have modified. You will see the O2 fractions over the height on different locations. And I will not go into the details of what we have modified in this learning process, but you can definitely see the improved distribution of O2 in this process. And definitely this optimized and modified distribution of O2 is surely linked to much lower emissions, a better carbon burnout, lower erosion risk, and so on and so on. So this is definitely what we can do today and how we do design today. The same, and I will skip this, is also valid surely for the cyclone design. We learned a lot also in doing different analysis on the cyclone and have introduced surely this what we have learned into our actual designs. As said before, in CFB, we have to control the emissions already with the combustion process. This is an advantage and a disadvantage. But this over 40 years, I guess we have learned very well. We know what to do. And these are the things what we have to do. We have to do a temperature control and air stoichiometry and also calcium to sulfur ratio. And all these have influences on the different emissions, as you can see. And very important, and this is something we have to keep in mind always. The temperature control in the CFB is really the key issue for the control of all the emissions. And I have to say, there are typically sometimes cheap CFB designs available on the market which do not have any temperature control. And this typically provides a lot of problems in the operation as well as in the emissions. So coming now to low emissions and how to achieve low emissions. As I said, these kind of standard CFB designs, which have a limited air stacking, no temperature control, and no absorbance condition, you can see what they can reach. Typically, the yellow highlighted is what we offer as our standard today. So we have surely also, thanks to the help of the CFD investigations, we have an optimized air stacking, we have a temperature control. We can reach already typically less than 200 milligram of NOx without any additional measures. The sulfur content truly is depending on the local limitations and on the limestone addition and on the sulfur content in the fuel. Typically, we can reach 100 milligram with only limestone addition, nothing else. We can offer an ESP or a backhouse filter, and you can see with an ESP we are well below 40 milligram. With a backhouse filter we are typically lower than 10 always, but let's say in a range of 10 to 20. In case, due to whatever reasons, you have to limit your emissions any further, there are still measures to reduce the emissions. And the last row shows what we have to do in Europe in case we design boilers, CFB or whatever type for waste, RDF and other things. So we have to reduce any further. All this is available and can be added to CFB as well. Okay, this we have seen already, so I will skip this. I will also skip this just to come to the end. So the advantages of the CFB technology have been explained several times today. Low combustion temperature, typically lower than 900. And as I said, quite important, we have to control this. The highest fuel flexibility, which ranges from petcoke to RDF, is only given with CFB. A uniform temperature distribution. We do have almost no formation of thermal NOx because of the controlled temperature. We can do in situ SO2 capture just by the addition of limestone. We do have a very good fuel and air mixing conditions, and the thermal inertia in the CFB is quite less and quite sensitive, less sensitive compared to PC. So we have a very uniform temperature release, which makes CFB very, let's say, the best option for USC designs. So coming to my last file, yes. So the conclusion and the outlook, and maybe we will have the chance in some questions and discussions after my after the final presentation. So CFB, from my point of view, is the most flexible combustion technology which is available on the market today, especially with regards to the fuel flexibility, which for the operator is very important because it's related to operation cost over many years. The CFB provides the highest efficiency and still having lowest emissions. Biomass combustion or biomass co-combustion reduces the CO2 footprint of a plant, and in many countries already a CO2 fee is in place. And I'm sure you're looking just at the weather phenomena of the last years, the CO2 fees will come up more and more also in Asian countries, and the operators today have to start to think what to do to reduce their CO2 footprint. Existing CFBs can be easily upgraded to biomass, this was demonstrated, and the biomass addition to a large-scale CFB is more safe, flexible, and efficient, and even economic than just building one small-scale CFB for biomass only. Yeah, I guess so. That's it for the time being, and I hope I could give you some interesting insights, and maybe even could add something which have not been explained in the before presentations. So thank you.
Thank you so much, Mr. Frank, for giving us detailed technological development that Doosan has done, the CFB technologies, and of course, giving your views for future CFB combustion technologies. Our next speaker is Mr. Lakshmi Narasimhan from BHEL. Mr. Lakshmi Narasimhan, can you share your screen? So he will be talking about scaling up higher capacity CFB systems done by BHEL. I think you need to unshare your screen, Mr. Frank. Your chat window is...
I think I did already. Let me just check again. At least I tried.
Actually, your chat window is shared.
You have to stop the presentation.
But I have. Well, maybe I have to close the presentation. So, but it's not shared anymore. No.
Yeah. Now
okay.
Yes.
So sorry.
Yes. So, Mr. Lakshmi Narasimhan, you can share your screen now.
Yeah. The presentation to everybody.
Yeah, we can see your presentation.
Yeah. Yes. So the last presentation from BHEL side, and I thank the previous presenters for making my job very easy. So I have to just make a concluding presentation, and I am very conscious of the time. I will try to complete within 10 to 15 minutes. So I had structured the presentation on 3 aspects. Why we are here, in the sense, clean cone technology, why it has been from the industry point of view, and what BHEL has done so far, and what we are having in the future. So this is as simple as it can be. This slide, our chief guest had also indirectly indicated all these slides. So we still are dominated by coal, and that coal is a very damaging word right now in the world, that it is causing all the CO2 emissions. We have to be responsible, but we'll have to see how the technology transition happens. Right now, as previous speakers told, we have got good SOx emission captures. NOx emission, we are able to have a good capture rates, even mercury. But what about carbon capture? Professor Bolekner onwards, they have been telling about how the developments are happening. So I will not go into the carbon capture part of it, but I will talk about what are the intermediate stage in which we can leapfrog the technology. If you look at the Indian context, how the thermal energy has been growing, you can see a predominance of coal, which is now coming down in the past decade. So this is a very good news as far as catching up the world is concerned. But then, having said in the bottom slide that the capacities are growing, but the contribution for the past 10 years, it is getting almost stagnated. That hype of increasing renewable source is not happening. That lifting, the heavy lifting, has to be still done by the coal. So looking into the future, as our chief guide also introduced, even though our capacity is going to shrink from the high levels of 60s or 70s which we had, but the contribution is still around 50%. So our immediate responsibility as a technology provider and a supplier needs to address this particular aspect, that we take in the biomass and the coal in a proper mix. So I'll come very closer to my home state, Tamil Nadu, because this state is very much endowed with high levels of renewable energy, very similar to probably Germany. We have a high wind power source as well as solar. So if you look at the decadal change which is going to happen, the coal capacity utilization is going to come down to 40%. The percentage is a very misleading number. I'll explain in the next slide. Whereas the renewables is going to go up as well as nuclear is going to go up. Because this particular aspect, Professor Boalaknar was asking, probably I'll answer it. Yes, nuclear energy also we are in a very expansive mode, but then it won't be reaching the levels of renewables or coal. That is the answer for the question. But if you look at the decadal change, the 30 gigawatt of installation is generating around 97, can generate around 97 billion units of power. But still it is dominated by coal, which is giving around 70%. We are expecting that renewables installation is going to go up from 36 to 57%, but the contribution is still questionable that 40% is going to come from the renewables. Still coal is going to be around, even with the shrink to the level of 30%, we are supposed to do the bulk lifting of power. This is very important from energy security point of view and to sustain the entire industrial hub which Tamil Nadu southern states have developed. So coming to the contribution what BHL has done so far, it is only a history, so I'll just run through very fast. We have nearly contributed 160 gigawatt of power and predominantly PC fired boilers. You could see a very small growth of CFB boilers. Of course, you can add all the competition also that this will never reach the PF boilers. The experience generated in PF boilers is quite high, and that is also a good thing as well as a negative thing in the sense most of the operators are very much used to PF boilers compared to CF boilers. This is one area in which all our team has to contribute in educating and coming back. Coming to fluidized bed combustion system, we have really started way back in 1970s when we did a small test facility here, and we have come up to this stage, selling nearly about 101 boilers, 25 boilers of CFBC and 66 of BFBC. This figure is very important is because less than 10 megawatt, we did a biomass, 100% biomass way back in 1994. So BHL has that experience way back in 90s when even people didn't talk about biomass in India. But then as the chief guest told, the economics drives the entire utilization. So when they started seeing power plant purchasing rice husk and paddy, the cost of paddy and rice husk was increased by enormous, making the power plant very ineffective. I mean, not competitive compared to coal fired. So this was the history I wanted to keep the perspective for the new Indian audience. So if you look at the scale up happening with our bubbling fluidized boilers, we roughly scaled up by every 3 years or 2 years. And we have reached a capacity of around 35 or 180 tons per hour, which is the maximum capacity right now with the bubbling fluidized bed boilers. And we did some few exports also. But this experience is nevertheless very important when it comes to understanding the bed dynamics, how the bubbles are going to be there, what sort of fluidization velocity we need to have. All these have given us very strong foundation when it comes to scaling up the boilers. So with the confidence we can say that we have done up to 200 tons per hour. We can handle any upwards of 1500 kilocalories per K. And interestingly, we are able to handle hash up to 65%. And as somebody was trying to utilize waste of somebody, we can try to utilize or we can utilize ESP coming from power plants further to reduce the unburned carbon in some of the fired boilers, which I also seen where the imported coal is very high. Unburned carbons are crossing 6 to 7%, restricting their usage in cement plants. Those sort of things can be burnt here further nicely. Coming to CFBC boilers, and I thank Frank Leishike for explaining all the features of our technology also. We had a collaboration from 93 and ended in 2003. After that, we have been jointly working for Neyveli and Bhavnagar. So that also the scale up happened very fast. So to put a perspective of Indians power plants in the global thing, of course, I thank Foster Wheelers people to represent the South Korean plant. That 550, they have scaled up really nice. We are also coming in the same majority of the cases where the power plants are there. We are also come up to that. Interestingly, a very similar capacity range which we are having reference as of now. And I am just pointing out two different varieties of lignite here. I will come to this aspect slightly later. So if you look at the offerings which we have almost the technology which people are talking, except for few variations. Interestingly, all the integral FBHE and pant-leg designs have been jointly worked with Doosan lenses, earlier lenses. One interesting aspect I would try to tell as part of CFBC's conference is the importance of cyclone efficiency. People had initially thought that cyclone is a very static device and it can be not contributing very much to the process. But we have learned in a very hard and better experienced way how cyclone efficiency improves the whole process. I was not knowing about the presentation of the CFB materials group, how important or how costly the material is there at Europe. If you really see, a proper cyclone design would save nearly 3,000 tons of bed material if you properly designed. That is very important, and we customize our design based on the fuel. As Frank Leuschke was also mentioning, we need to be very clear about the fuel for which the boiler has to be designed. That being known, the most of the cases, we will not have any surprises. So BHL has not only been selling boilers, but we have been very extensively developing an ecosystem through industry institute interaction, right with NITs and IITs. We have, instead of fortunately having interaction with our erection team, also with our manufacturing team, and extensive fuel testing in our test facility. So all these things are going into our product design by means of operation feedback, operation philosophy. Why I am putting stress on the term operation feedback and operation philosophy is most of our industry here are very much attuned to PF boiler operations, and they are not very much conversant with CFBC systems per se. This needs to be very much improved upon to ensure success of CFBC, as Chief Guest was rightly pointing out. So we did have a CFBC test specialist right before we started the collaboration. So we were trying to scale up with a good knowledge base. And as Leuschke was telling, we do also have a similar simulation scale where we are trying to predict where the erosion rates are going to be high and suitably design our cyclones and other areas of boilers. One of the key point of this presentation would be this aspect, that many lab scale models or pilot test facilities will not reveal the surprises, because BHL had, as a company, we venture into areas where fresh coal lignites are being sourced. So even though many tons of material test lignite have been fired in our test boilers, different seams of lignite seems to come, and we had different issues on different sites. For example, in Giral, even though the design initially was told around 4% sulfur, we were getting almost 6% and exceeding 7%. Problem was never with the fuel, but with the limestone. So the limestone which was available locally had a very finer particle attrition. So this had resulted in recarbonation issue. In fact, instantly that topic was explained by professor with about the equilibrium conditions in the calcium oxide and carbon dioxide diagram. So all these things were resolved, and we have completed the performance test and handed over. Next is Palana lignite. In fact, we had a very different issue there. Even though the same phenomena was noted, the centering aspect, but the issue was something related to the chemistry of the ash, that two particular seam of the lignite. So such being the surprises there, even with lignite. So that is what I was trying to explain, that what the lab scale or pilot test will not show up is such variations which we needs to be carefully done. And since the design is very flexible in the terms of adjusting the temperatures, we were able to easily come out by adjusting the operating mode, which incidentally is one of the features which BHL offers. Next, when we did the scale up to Neyveli lignite, we had a very significant issue with pant leg operation. As I said, the boiler operators were very familiar with the lignite fired, PC fired boiler systems, those people. To convert them to operate into plant like with balancing the tons and tons of recirculating acid, it's not a simple thing which required a very robust auto controls to be established, which we are able to establish. Then most of the one of the important aspect is refractory. Even though we can reduce the quantum of refractory in CFBC boilers, we cannot totally avoid it. And refractory has a different characteristics. It depends on the raw material available in Europe as well as in India. There is a lot of difference. So this differences needs to be really understood, and we have really understood, worked with our suppliers, and we have understood which particular refractory will have characteristics for the Indian conditions. And then we have a very interesting aspect of external FBHE, one of the largest in world, I would say. And we had a very experience of issues there, and we are able to successfully come out with a modified cooled support. This particular system will be very useful when we are going for a OTSE system and other scale-up issues. So interestingly, when I talk about OTSE systems, we do have a test facility here to optimize the rifle tube configuration, especially for CFBC boilers. This is very important, considering that our boilers not only need to be able to accept biomass fuels, but also operate at part loads in view of rising renewable injection in the grid. So this particular aspect has been already taken up by BHL, and we have fairly established the profile. To give you a reality picture of the intermediate thing, we have already worked on, and we are pitching upon 350 megawatt designs, because we see a lot of retiring 210 megawatts and 250 megawatts in the future, which have been added in late 80s. So we already come up with the thing, and a small extension alone would be required to fit in the existing CFBC, OTSE CFB boilers. So we already have a plan in place according to our government's vision, and we are ready forward to go ahead with this. And the other carbon capture strategy which we have talked about, and integrated combined gasification power, I think Chief Guest has told more than what I wanted to tell, but we wanted to give a latest update that we are ready with this design. We can even scale up to 182 megawatt. Only issue is, as somebody was also highlighting, the commercial motive has to be there from the users from power sector side. So we are ready with the product. We have a gas turbine running there with syngas for quite some time. We have very good operating experience, good carbon conversion efficiency, which we are seeing there. As a offshoot of this IGCC technology, we have a CFBC based industrial gasifiers. The biggest advantage is we don't have any TOR or phenol. We have a good flexibility in turn-on operations, which is required for any industrial system. We have higher throughput compared to end-to-end system. That is the biggest advantage we have as a technology provider for this particular thing. And it is, as everybody was pointing, it is very much highly suited for Indian ash coal. So coming to the end of my presentation, so clean coal technology, there is no mistake about that. It is a need of the hour for the entire decade. Still be stabilized with the other source of energy source. We have contributed both in terms of combustion system as well as gasification mode, trying to pioneer the system way back from 90s. And because of our efforts, we have been able to develop an extensive ecosystem. Example, the refractory manufacturers were very much appreciative of BHL's support in developing, because they are able to sell to other plants, including many other companies. So such an ecosystem was being supported by BHL so far, and we are really working with our customers and to develop and to be ready for the future. Thank you for your time, sir.
Thank you so much, Mr. Lakshmi Narasimhan. I think this was also very insightful for us, getting the perspective of the Indian industry on CFBC technology and seeing that there's a lot of interest. Next, I would like to invite Mr. Vinod Kumar from the Indian Power Management Academy.
Hello, can you hear me?
Concludes my presentation.
Yes, Mr. Vinod Kumar, yes.
Oh, you are able to hear. Thank you so much, Professor Krishna. First of all, good evening to everybody from India, and afternoon in to Professor.
Hello?
Yeah, we can hear you. We can hear you. Please go ahead.
That concludes my presentation. So thank you for it. Yeah.
So good evening to everybody from India, and afternoon to Professor Bo Lechner and other colleagues, and good morning to some of friends that who joined from USA. This virtual program, I, on behalf of IPMA, thank to Professor Ravi Krishna, Pratiksha Panda, and the entire faculty of IISc led by Professor Pradeep Datta, who have made this program to mature at this time. And I can see something about 90 people is still in the locked out program for at this time. When we started, it was almost about 150, and that directly speaks about the people interest. Since it's a time when we have a dinner being ready at home, and particularly only those people that who are really very much interested to continue with the subject. Coming back, not taking much time, to thank you once again to IISc. And it's nothing else and nobody else could have probably presented the importance, the usage, and the future technology and the options other than by Dr. Saraswat himself. Dr. Saraswat, as my co-chair, Dr. Panda, he's already said, and Professor Ravi Krishna, that he is a member of India's highest planning body, Niti Aayog, and noted scientist and technocrat. We had, since morning, we had a great listening and the lectures from Sweden, various professors, Dr. Lechner, Dr. David, and other colleagues. The people that who logged in from Finland, they had been extremely nice to have spare time to share some of their thoughts, and particularly on the biomass burning. When we are starting about this program, I would just like to say that Dr. Krishna and I had worked out how to bring the industry around this program. And thanks to him, his efforts, that this program has today matured very, very well. Further to that, ladies and gentlemen, one must not thank at this moment to the efforts that Swedish, the Indian embassy in Sweden, that they became the catalyst to bringing Professor Bo Lechner, Chalmers University with IISc, including the people from the DST in New Delhi. They have been a great help to bring this. Why these are very important? And for this, I have made a small slide, and I'd like to show, and hopefully that it will be very, very short, and let's see. 1 second, sir. Where is that? Share. Yeah. 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 Open.
Softly. Taking time.
Yeah.
So it's taking time.
Yeah.
I'm sure.
Oh. Come on. Yeah. This one? Yeah.
It's not open. It's not open, sir. Ask people.
Can you look at? Yeah. Can you hear, sir, and see this slide?
We can hear you, but the slides are not visible yet.
Oh, okay. So no?
Not yet.
Not yet. Okay. So probably I'm finding it difficult. So I'll go ahead and speak as it is.
Mr. Ravi Krishna, can him email, then he will share.
Yeah, probably.
We have seen these slides like for seconds, and again it disappeared. I was wondering if you can try once more. If there are too many PowerPoints, you can just switch off all of them and just keep the presentation. Sounds to be loading. Yeah, it's clear right now.
Okay, thank you. So we have had a lot of discussions, particularly on the success of the CFBC in Europe. But when it comes to India, I had just made a small, what are the constraints that it has been? So right from the beginning, that we had a bias towards the old operational records of utility CFB boilers in India due to refractory failure, bottom ash issues, etc. And then there have been a quite mindset against the CFB boilers. And that is why we see not much of references in the utility sector. No reference of CFB boilers in NTPC. That has been one of the major, in my opinion, the reasons that why the CFB technology has not taken off. And then lack of commitment and seriousness towards the emission control as a whole when it comes to the emissions. And mind you that India did not have any kind of emission control limits or compliances to be met officially before January 2016. And then complacency, comfort and convenience with the PF boilers. Lack of in-depth study and efforts to change in accepting facts on technological advancement made on the CFB boilers, whether it's a USC or SC CFB boilers, co-firing, then limited R&D work on fluidization and lack of training. And this is where and the disconnect of industry with academia in general. The last 2 points I would like to just say, thanks to the efforts of Indian Institute of Science, bringing it together, the learned professor from Sweden. At that time, for the course from 25th of January to 4th of February, there were 20 people who had registered. And by the time the program started and we got into it, then it only remained 30 people. And out of which there have been many from the academia. So the industrial cooperation, respect to the participation, the interest has been rather very low. And similarly, the technical institutions, they have also not been coming up because of the fact that not much of work has been done on the fluidization. And why it has not been done? Everything depends upon the market. And is the market ready to pay to hire good engineers, good technicians, good academicians? And that is one of the subjects that I would like to bring it here. As Dr. Saraswat said, and it is my request to IISC that they should present it to Niti Aayog and saying that a couple of CFD combustion power plants in utility sector with the supercritical parameters may be taken up at the existing premises where old or closed power plants stand today. Fuel could be coal and biomass and mixed together. Niti Aayog themselves will have to pilot the above plant, since no bankers today are ready to fund any coal-based thermal power plant otherwise. Large industrial houses, OEMs, and utilities like NTPC may join hand with the IISC to set up a pilot plant on CFB combustion for industrial and academic pursuit to make India Atmanirbhar, which is a slogan given by our Honorable Prime Minister. In order to reach to that and to strive to achieving towards a circular economy, these technologies, CFB, oxyfuel, calcium looping, chemical looping, CO2 capture, and the gasification he himself has talked about in a very widely addressed seminar by the Prime Minister himself, and therefore it is my and incumbent upon the industry of India that they should join hand to make this. If you have seen that since 1970, Dr. Bo Lechner and his professors, they have been working and they developed the CFB boiler of 12 megawatt in their lab, and I happen to be, shown around that plant by Dr. Bo Lechner. It shows that how much work they have done it, and today we are very, very fortunate that even at almost about 7:45, the people are listening. And my request would be, Dr. Bo Lechner and Professor David, to please continue your patronage to the university. This I discussed with Dr. Bo Lechner, and he says, Vinod, it would have been extremely good if there would have been a face-to-face meeting. And this would have been in IISc Bangalore in the natural setting and in the clean environment. Then I have told Dr. Bo Lechner that we would probably have it in the coming year or so when the COVID is gone. This is my, just opening the remark to start the panel discussion. Ladies and gentlemen, you have learned, you have heard many speeches. I don't want to go anything further, excepting that I'd love to invite some of the people that who are already listening and that they have been listening for quite some time patiently. It's very interactive. So from my experience, I have seen some of the power plants which are very successful in CFB operating, and let's listen some of the success stories, because professors who are joined from abroad, particularly in Europe, they should be able to listen and listen. So in this respect, I have if Mr. Dikshit Patel from Reliance Industries, are you on there online, Mr. Patel?
Yeah, I am on. Can you hear me?
Oh yes. Okay, so Mr. Patel, could you just, you are located at Dahej, if I believe? Yeah?
Yeah, I am located at Dahej.
Okay. So, Mr. Patel, he has been operating, yeah. Hello?
Yeah.
Hello? Yeah.
Your voice is getting down.
Mr. Patel, you can share your availability record benefits that what you have achieved out of the CFB plants that you set up 9 units of 500 tons per hour boiler in Hazira and in Dahej.
Yeah, good evening everybody in India, and I hope it would be noon at German places. And again, thankful to Vinod Kumarji and his team for arranging this session on exclusively for CNBC in Indian context. Now, to share experience at Reliance, we have almost 9 boilers of 500 ton and operational since 2016. All our boilers are operated on imported fuel, and depending on economic viability, the fuels are imported. Since 2016, no major problems have been observed at either of our boilers, and we are even operated boilers more than 600 days continuous operation at Hazira. Neither major erosion, fouling, or any clogging has been reported so far. And this is the, I think, benefit of CFB boiler if it is designed and operated the way it is built. So far as emission control, temperature control, all the designs have been built in the CFBC supplied at Hazira and Dahej. We have a limestone control system, bed material control system to have temperature control. And then based on our learning experience, we have tried with different types of material as used as a bed material also. So that today, as in the context of India, CFBC, yes, is a learning curve for everybody. And the experiences shared are being greatly helpful in achieving the confidence and usage of these utility boilers and high scale boilers to ramp up the power need of the country. Now, as discussed in major of the slides and whatever presenters have informed of different companies, in Indian context, what would immediately help is how would biomass be handled in the current coal and coal handling system or fuel handling system, we may say. Because when we say of a mix of 10 to 15% can be used, because I understood from all the manufacturers that their boilers are designed to meet 10 to 15% of the biomass straight away. So what would be needing is how industry would be benefited in using those biomasses in the required form of size of boiler, whether they would be needing independent handling system to feed biomass, or whatever system is designed can as it is be used to feed biomass into the boiler, because as known, CFBC is flexible in terms of size and as well as GCV or fuel changes. So I think in the immediate scenario for the decade, whatever fuel flexibility or options we use in using biomass as a mix would be a great help, and the manufacturers need to come up to help the end users. As far as we as end user would be thinking of getting the maximum benefit in terms of getting the biomass used and meeting government's immediate objective of 10%. So I think Vinod Kumar, this is what I feel, and I am thankful to everybody who are present over here, and a lot of thanks especially to the Sweden team who has put up some of the important views on agglomeration and fouling factors. And the new thing what we had also been educated is of the different type of bed material which can be used as a alternate source. But yes, what would be the economic viability needs to be looked into. But it's an option, and I think all the industry users would have an open mind to see how it can benefit in overall context of the country. That's all, Vinod Kumarji. Thank you.
Yes. Thank you, Mr. Patel. But I just need one thing, that what has been generally your availability of the CFB boiler during
99.9%.
Okay.
We didn't have any forced outage. We didn't have any tube leakages, no trippings. Whatever shutdowns were plant shutdown for IBR. We are the boilers are so reliable that we are able to do IBR twice, means once in 2 years.
Is that a performance for any particular unit, or it's generally for the station for all 9 units?
All 9. I'm talking of all 9 units.
Okay. Thank you. Thank you so much, Mr. Patel. Thank you for enlightening the entire community that who are listening to your presentation. Thank you so much. Now, I'd like to check if Mr. Radhakrishnan from Walmet, is he available during this program? Oh yeah, Mr. Radhakrishnan. You see, your company, Walmet, has done a lot of pioneering work, and I was reading in one of the journals that Walmet earlier days, they set up the largest CFB plant with a biomass in somewhere in Finland for power industry. Would you be kind to just share some of the ideas that what you have with respect to the biomass and experiences with respect to CFB in India? Can't hear you. No.
Unmute his mic.
Please unmute your mic.
I am already unmuted. Am I audible now?
Okay. Yes. Fine.
Okay. Good evening to all the gentlemen. Good morning from US and good afternoon in our own neighboring country, that is in Sweden. My name is Radhakrishnan and I'm representing Walmet. And basically in Walmet, right from the day one, we were concentrating only on the CFB solutions, I mean, the fluidized bed solutions. So our activity started somewhere in the early 80s, like when the new generation combustion technology itself was evolved. And right from day one, we were concentrating on combustion of the special fuels, mainly this agro residue or biomass or waste. So of course, coal was never a preference for us at any point of time, because keeping in principles of Finnish government that we wanted to be always carbon neutral. So that way, of course, I don't say that we never design a coal-fired unit. So that depends purely on customer requirements and especially limited to Asia Pacific regions. So as far as our experiences, I wanted to just share only one slide about it, if it is okay for all of you.
Mr. Radha?
Yeah. Am I audible now?
Yes, I would like, if you could be kind to consider the time.
Yes.
Marketing of the product and the company should be avoided at this time.
No, it is not regarding marking, but basically the question what was asked about the complexity of biomass. So at least we have developed these 4 concepts. For us, of course, coal burning is a very easiest one. But when it comes to biomass and waste, yes, it do have a lot of challenges in terms of the alkalis being present and also the other impurities. So that way we have got a good experience in terms of that. And when it comes to waste, for example, obviously you have all these heavy metals and things like that. So considering all these things, we have developed our technology. And as far as India is concerned, which you are asking, basically we know that CFB is an excellent solution, because personally I come from a PC-fired background in the past, but for the last 5 to 6 years I've been working in CFB solutions, and we do find that it is very, very effective in terms of today's challenges, especially when you have this fossil fuels being to be totally eliminated or reduced. So then the challenges for new fuels day by day is increasing, and burning of this is always difficult. So another point which I would like to highlight to you, Vinodji, is when you said about representing to Niti Aayog about promoting the CFB solution itself, I would like to make a request to you that for even for waste firing, we should consider CFB as a better solution, because today's existing technologies, again, I don't want to name them. I'm not telling that they are inferior, but CFB can offer a better solution because we have developed the waste solution where we can achieve a high steam parameters of say 100 bar and even 500 degrees centigrade. So that means we are respecting the waste also. That even waste should be treated as a fuel or like a gold. It is no more a waste. So considering that, and especially when we have so much of focus in our country for this waste to energy, probably CFB should be considered as a better solution.
Thank you. Now I'd like to go back to Mr. Lakshmi Narayan from BHEL. Lakshmi, are you there?
Yeah, very much there, sir.
Thank you very much. You see, this country has largest contribution with respect to the coal PC-fired boilers from BHEL. And you have been talking about CFB. Why there have been, that BHEL failed to take up this issue with the top planners, including with Niti Aayog, that when the CFBC boilers, they come with inherent property, technical advantages, that you don't have to add NOx, the SCRs, you don't have to do any FGD, and you can make this in a smaller compared area and keep the compliant of the emission level and other pollutants under control. And still, I don't see that BHEL did a very good job with respect to promoting the CFB technology when it comes to particularly after the 2015, when this Gazette notification for the emission controls came into being as a statute. Thank you. Would you respond, please?
Yeah. So there are three major reasons for this particular aspects. One is it is driven from the national perspective, that we have a very high level of ecosystem of PF boilers which need to be taken care, because they cannot be shut down in one day. So BHEL's first priority was to ensure that nation is fed with the reliable energy by converting those stations into complying with the requirement. That is the topmost priority as it comes on the agenda. The next particular aspect about taking up the CFBC, as somebody pointed out earlier, we had several rounds of discussions with NTPC, the major utility user. They in fact had a very strong O&M team commissioning our 125 megawatt, supporting our commissioning in 125 megawatt CFBC boiler way back in 2000s. But then those experiences were never followed up, and they always CFBC was on the sidelines, to be very frank with the whole discussions here. So that was the second reason. The second biggest utility didn't view the CFBC technology very favorably. Third thing is, I would be more frank telling that all competitions were trying to tell the negatives of each other's technologies, in turn hurting the whole image of CFBC. This is one very subtle but a very strong message, which I have learned very point of fact, especially from NTPC top management, that you tell your technology is good, the other person is telling their technology is good. But never there was a strong team, as you have been organizing a lot of CFBC conferences wherein you allowed everybody to present their views. A joint effort, in fact, by even as late as 2017, we tried to do that. We tried to make a presentation to NTPC and the CEA, and trying to tell how the CFBC systems are now stabilized. You can look at the references even in India or in Europe or in elsewhere, that how things are stabilized now. Earlier there were issues and we had overcome that. Now, but then once bitten, twice shy. So NTPC is still not convinced fully, I would say, from my interactions with them.
Thank you very much. Is there anybody from
It's just a question. May I add to what Lakshman said? one other issue is quite important for India to know, because typically the operation results are compared from easy burning fuels in PC with difficult burning fuels in CFB. So most of the CFB plants designed in India up to now have been designed for fuels which even cannot be burned in PC boilers. So this is also some issue you have to take into consideration.
Thank you, Frank. But if you look at the industry side and the usage of and the population of CFB boilers, I think it's a pretty good, because something about 400 boilers contributed by all the 4 companies: Thermax, ISJEC, Tyson Group, 3 major that who have been player in the industrial sector, and supported by also BHL in some of the cases. And they have demonstrated pretty well on this matter when it comes to contribution of captive power generation and reliable power generation through the through CFB, including in the I must not shy away when I talk about the JSW plant in Rajasthan, Barmer, which has been using 8 of 135 megawatt, and they have been doing pretty well. And you don't hear much of a problem with respect to the operational aspects. And therefore, the industry side, as far as the CFB, they have done very, very well to my knowledge. And only it is the utility sector which had lagged behind, or properly, or maybe we should say it was a step-brotherly relationship with respect to the CFB boilers in comparison to the PC-fired boilers. Let me move to anybody if there is from Thermax or ISJEC that would like to share their views. Is there anyone from ISJEC? Okay, no, thank. Or from Thermax.
Vinit Kumar, this is Professor Ravikrishna. So yeah. I think I just wanted to react to some of the points that the panelists that you invited have made. So I think, yes, there are concerns, as you rightly pointed out, about CFBC not being taken up so aggressively in India. But I think it's good that we had Dr. Saraswat today in the in the workshop, and I think he understands the importance of CFBC going forward as part of the clean coal technologies and biomass co-firing. So I think it's going to be, I think going forward, I think we can really see that CFBC will gain more and more importance. And I think all the participants today, I think, as you rightly said, because of COVID, we have been forced to meet online. But in the near future, I think we can definitely meet physically and really take this forward. So I think I would just request maybe before we close, my colleague Dr. Panda to share a slide where I think this could be a starting point for taking this forward in terms of having a sort of a demonstration kind of a pilot plant at IISc. So maybe I'll leave it to Dr. Panda to say a few words about this.
Yeah, thank you, Mr. Vinod. Thank you, Professor Ravi. So I think today was one of the very fruitful sessions where all of us were very fairly well got educated in the technology of CFBC, its challenges, particularly while oxy-fueling the CFBC, using the capability of CFBC in terms of fuel flexibility, all the way from different grades of biomass, and what are the main challenges, how CFBC can be useful in emissions control, and then finally carbon capture. So some of the very key and very important points have been brought out, and we got all educated from esteemed academicians, researchers, scientists, and industrialists. So taking this the way forward for us at IISc, and taking this relationship between India and Sweden forward, I think the next step that we want to propose is to build this pilot plant, CFBC based pilot plant, which could be something of the order of 50 to 100 kilowatt, which can be designed solely for academic research as well as for understanding some of the key challenges which can be useful for the industries to understand the technological advancement. Particularly, I think we want the capability to have an oxy-fuel mode to demonstrate clean coal combustion technology with the carbon capture and utilization, and then also explore feeding it with biomass or MSW. Of course, we have seen that there are several challenges associated with biomass that we need to be aware of, and this pilot plant would be a very good way to understand these challenges. So at this point, I think it will be great if we could have a good industrial collaboration in setting up this pilot plant at ISC, which could be the way forward that we can see, and hopefully it becomes one of the major power producing technologies in India in the near future. So that would be the concluding remark. Professor Ravi, if you would like to add something to it.
Yeah, I just want to this is more like a vote of thanks. I just want to thank our colleagues from Sweden, Professor Bo Lechner and Professor David Palaris, and of course all the speakers, and special thanks to Mr. Vinod Kumar for really bringing in a very strong industry participation to this whole workshop. So I would like to thank all the speakers and all the participants, because they have sat through almost 5 hours of continuous lectures and interactions. So a real big thanks to everybody. And as I said, we hope that a future event on this can be held in person in India, once all this COVID issues have been resolved. So, but yeah, I think I would just like to thank everybody, and we will reach out to some of the industries who have participated today for their possible participation in helping us set up this pilot plant. So we will be contacting you shortly, and we will be in touch with you. So again, thank you all very much. And again, I would like to thank the chair of the session, Mr. Vinod Kumar, for having really brought in more perspectives that were missed out. We couldn't really accommodate all the industry because of the tight schedule. So thanks to him for really bringing in a lot more industry perspectives during the panel discussion. Thank you all very much.
May I make a last comment?
Yes, Professor Lechner would like to say something. Please go ahead.
Yeah, I would like to prolong the workshop by saying a few words on my impression on fluidized bed combustion in India. I notice some important things. You have a local coal, which is more suitable for fluidized bed combustion than for pulverized coal. So that is a very strong reason to focus on circulating fluidized bed combustion. The other thing that I notice is that there is a growing interest in using biomass waste fuels alone, or as you have emphasized, some of you, together with coal in co-combustion. And again, circulating fluidized bed is extremely useful in this respect. So I just wanted to emphasize this. I knew this from before, but I notice as an impression from this conference that most of you or all of you agree on that. So I can only wish you success, and I can only wish also the future successful development of fluidized bed combustion in India. Thank you for your conference, and it was very nice to be able to participate.
Thank you, Professor Lechner.
Thank you, Professor Lechner.
Thank you. Okay, I think sorry for going a little bit behind schedule, yeah, we couldn't really take questions on the talks because of the very tight schedule, but I think we would encourage the people to sort of write to us on their feedback of this workshop. Maybe they can even write to us on any technical queries. We will definitely try to facilitate, answering your queries or, and getting back to you. But do write back to us and we will try to keep in touch with all of you.
Professor Krishna, just one last
Sure.
question from my
Sure.
side. Many people have approached to me to just check from the industry whether you are going to post these lectures on your website, or you will share with the people that who have joined here. Please do consider, and you may confirm to them later on if you wish. Okay.
Yeah, so we have an email group of all the people who have registered. So we will explore creating a sort of a YouTube video of today's proceedings. We have recorded them. We will try to get a YouTube video and send the link to all of you. Unless I don't think any of the industry participants have shared any confidential information. So we will first check with all the industry speakers. If they are fine, then we will not have an issue sharing the video of today's workshop on YouTube with all the registered participants. We can do that. Okay, I think if there are any other comments from anybody.
I see that Mr. Zayud, he has been here in this conference since very beginning, and I would like just maybe a couple of minutes, and then you can officially close the seminar.
Sure. Yes, please go ahead.
Yeah. Hello, everyone. I would like to introduce myself. I'm a doctoral engineer at UCL, Catholic Université de Louvain, and I have already done my PhD on the oxy-fuel combustion at the Indian Institute of Technology in Guwahati, with supervision of Professor Peniswakar Mahanta and UK Saha. And I came here to Belgium to continue my postdoctoral research. Actually, this meeting is quite helpful, and I would like to thank everyone, and even Professor Davide. Actually, I would like to mention a brief thing about Professor Davide. When I was doing my PhD at the Indian Institute of Technology in Guwahati in India, I have faced some problems, and I asked for inquiry from Professor Davide by that time. It was around 2012 or 13. And he welcomed my question and even agreed for Skype meeting during this time to clarify my questions. So maybe we didn't have time later on to meet, but I hope that you are doing well, and the rest of professors. And I wish all the best for this project and between ISC and Chalmers. And looking forward in future to cooperate with both sides. Thank you very much.
Thank you. Thank you for participating. Thank you very much. Thank you. So I would like to now close this workshop. Thank you all again for wonderful participation and your patience. And as I said, this is not the end, this is the beginning. We will be in touch. Hopefully more such events in person will be possible. And as I said, we will make the lectures or the video available to all of you once we get confirmation from the speakers. Thank you. So good night to my friends from India, and good evening to all the people in Europe. And I guess good morning to those of you from the US. So thank you all.
Thank you very much.
Thank you so much.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Lashkar. Bye-bye.